Yes, you can now enter your attendance. Enter your attendance now in the chat box. Okay, let's start. So today we'll talk about curl of a vector field. So when we talk about curl of a vector field, uh, a vector quantity which has a spatial dependence, which is not constant. Like A is a vector which is a function of x, y, and z. That means the component of the vector here, A1 can be a function of x, y, and z, and similarly A2 can be a function of x, y, and z, and similarly A3 they can be a function of x, y, and z, right? So if A1, A2, and A3 are not constant and they are varying with space variables like x, y, and z, then this is called a vector field. So when you have a del operator operating on that vector quantity vector field with a cross product in between, that operation is called curl. Okay, curl of a vector field. So whenever you have a cross product, like the usual cross product notation, you know that this del operator is this partial derivative with respect to x I cap, partial derivative with respect to y j cap, plus partial derivative with respect to z kk. So like the usual cross product, you will have to write I j k, and this first element del upon del x, del upon del y, del upon del z, and then a1, a2, a3. And if you do that, like if you take I here, and this is the, what is that? Shit, I forgot this term. Anyway, whatever it is, the term is, doesn't matter. So I cap coefficient will be this product, that is del a3 upon del y, and minus del a2 upon del z. So if you are having this vector operator, del operator on the left hand side, in this operation, do not write like a3 del upon del y. It's never like this. Okay. If del is the first operator, or the vector on the left hand side, the vector operator on the left hand side, this is a wrong notation. You should write it like del a3 del y. And similarly here, del a2 del z, not a2 del upon del z. It should be del a2 del upon del z. So be careful with that. And the coefficient for this j will be this and this multiply del a1 upon del z, minus this and this you multiply del a3 upon del x. So similarly, the coefficient for k cap you can write like the usual cross product. So this is called curl of a vector field. Now let us study this curl of a simple vector field, like this particular vector field, a vector. So again, let us draw what it is. Yeah, I think I've drawn this. Yeah, I don't think I have drawn this vector. I've drawn another vector. Minus of yi xj, yi plus xj. So you can draw this vector. Something like this. Let's say this is x, this is y, and this is, let's say, 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8, like this, for example. Now what is a vector at let's say 0 1? So at 0 1, the vector we will be having will be y is 1, y coordinate, this is x is 0, y is 1. So that means this is minus of I vector. All right. So x is 0. So at 0 1, what is 0 1? X value is 0, y value is 1. So this is the point. This is 0 1 point. At 0 1 point, what is a vector? We have a vector which is pointing along negative x-axis. So this is negative x-axis. This is positive x-axis is your I cap. This along this direction is minus of I cap. Okay. Upward direction is plus of j cap. Downward direction is minus of j cap. So at this point, you will have a vector having unit magnitude. I cap is unit vector, right? Having unit magnitude, but the direction is along minus of I cap. So you will have a vector like this. And at 1, 0, your A vector will be y is 0, x is 1 means j cap. So what is 1, 0? 1, 0 is this point. X coordinate value is 1, y coordinate value is 0 here at this point. So here you will have a unit vector pointing along the positive y-axis j cap direction, right? And if you are talking about, let's say, 2, 2 vector, at 2, 2 coordinates, a value will be minus of 2i, sorry, minus of 2j, y value is 2, x value is also 2, minus of 2i, sorry, minus of 2i plus of 2j. Now what is 2, 2? X coordinate 2, y coordinate 2, so the point 2, 2 is somewhere here. At this point, you have a vector along minus of 2i. What is minus of 2i? This is minus of 2i, plus of 2j, this is plus of 2j, and the resultant of this vector addition will be this. Draw a rectangle, and the diagonal of the rectangle will give you the resultant vector. And similarly, if you consider another point, minus 2, minus 3. Here, out here, your A vector will now become y is minus 3, right? Y is minus 3 means minus and minus is plus, so plus 3i plus x is minus 2, so minus of 2 j. So x value minus 2, y is minus 3 means x value minus 1, minus 2. This is minus 2 coordinates, minus 1, minus 2, minus 3. This is minus 3 coordinates. So the corresponding coordinate point will be somewhere here. Here you have 3i. 3i means in this direction 1, 2, 3. Sorry, positive 3i. In this direction 1, 2, 3. So you will have 3i vector here. This is your 3i vector. You have minus of 2j. So from here, minus 1, minus 2, minus 2j. This is minus 2j. Okay. So if you look at this, addition of plus 3i cap and minus 2j vector, it will result in resultant vector like this. So if you consider all the points here, what you are going to finally have is closer to the origin, you will have small vectors, something like this, small vectors rotating, but away from the origin, you will have larger vector, something like this. Okay. If you construct all the vectors represented by the vector field. So this is what you're going to get, something like this. Okay. So towards the origin, you will have a smaller magnitude vector, which is rotating. And away from the origin, you have larger and larger vectors with larger magnitude, but also rotating, like the way I construct. If you construct all the vectors for all the coordinate points here in the space, this is what you're going to get. Now, so we can see that this vector field, A vector field, is rotating around this origin. So, sorry, this is wrong notation. I'm mistyping. So A vector, right? So if you take a curl of A here, now, if you put a curl of A, if you remember, A vector is A1 I cap plus A2 J cap plus A3 K cap. Now you see that A1 here is minus of Y, A2 here is X, and there is no coefficient for K, means A3 is 0. So you have to put all those things. Instead of A1, you just put minus Y. Instead of A2, you put X. Instead of A3, you put 0. So if you do that, like if you use the Cal formula that I have written down here, if you would use the Cal formula by taking a1 as minus y and a2 as x and a3 as 0, then eventually if you calculate it correctly, this differentiation of x with respect to z is 0. Why is that? X is coordinate variables along x-axis, z is coordinate variable along z-axis. So the coordinate variables, x is independent coordinate variable, z is also independent coordinate variable. So z does not depend on x does not depend on z. They are just a coordinate variable. So the derivative here is 0. Okay. And similarly, differentiation of y with respect to z is 0, also z 0, because y does not have any dependency on z, because y itself is an independent coordinate variable along the coordinate axis. So, but if you differentiate x with respect to x, you get 1. Differentiate y with respect to y, you get 1. Minus into minus is plus. So eventually what you are having here is plus 2k, right? So as you can see here, if you have a vector field which is rotating around in a space, the curl of that vector field is finite, or it is non-zero. The curl of the vector field is non-zero. Right. Now, if you remember, this was the vector field we construct in the previous class. That is, a vector is equal to xi plus yj. So if you remember how we construct it here, yeah, this was our vector a equal to xi plus yj. When we construct it, we find that this was a diverging field. This vector points away from the origin, and as it moves further and further away from the origin, the amplitude of the vector or the magnitude of the vector increases. Right, this was what we constructed. So this is a diverging vector field. It, as you see, this is diverging vector field. It is not rotating at all. It's not rotating at all, right? It is just spreading away from one point of origin. There is no rotation of the vector field here. So if you take a curl on such kind of vector which is not rotating like this, so here this will be your a1, here is x, your a2 here is y, a3 is again 0, because the coefficient of k cap is 0, not there, right, in this expression of this vector. So x, y, 0. So if you follow the curl formula that I have given you, so this is what you're going to get. Differentiation of y with respect to z is 0. They are independent coordinate variables, so they are 0. And this is also 0. All of them are 0. And eventually you see that this is 0. So that means non-rotating vector field. Curl of non-rotating vector field. Curl of non-rotating vector field is always 0. If the vector field is not rotating, if the vector field is just a straight line, or if the vector field is not rotation, this will be 0. Right. So where is another example? We have given you another example over here, right? This was an example. The vector we consider here is a vector is equal to 1j. A vector equal to 1j. Let us take the curl of that vector. Wait, let me show you. Let me here. If you look at this, a vector equal to 1j, this is also non-rotating. As you see, this vector is just pointing towards the positive y-axis, right? All the vector fields represented by this vector is pointing towards the positive y-axis. There is no rotation of this vector. They are just pointing along the same direction. All the vector fields are traveling along the same direction. So if they are traveling along the same direction without any rotation, let's see what we get if we take a curl of that. So if I take a curl of this, a vector is equal to 1j. What I'm going to have here is that curl of a will be I, j, k, del upon del x, del upon del y, del upon del z, and there is no I term here, I cap term here, so the coefficient of I cap is 0, the coefficient of j cap is 1, the coefficient of k cap is also 0 out here. So if you do that, this will be I cap into this product is 0 minus this into this del 1 upon del z plus j cap, in coefficient will be j cap, this into this product is 0 del upon del x into 0 is 0 plus k cap. uh, K cap coefficient will be del 1 upon del x minus 0. So this is constant. Differentiation of 1 with respect to z is 0. Differentiation of 1 with respect to x is also 0. So all the terms will be 0. So that means if you have vector fields which are pointing along the same direction, like the positive y-axis in this particular example, without any rotation, then the curl is 0, right? And similarly over here, diverging vector field, we have the curl is 0. Only when we have a rotation of the vector field, then we see that the curl is non-zero in this case, in this particular example. So what is the physical meaning of a curl of vector field? So when you perform this curl operation on a vector field, what does that mean, right? So you can see that by now, I think everybody now understands that curl of a vector field is a measure of the rotation of the vector field. Okay, if the vector field is non-rotating, then it is 0. If the vector field is rotating, then it is non-zero. And depending on the rotation of the vector field, curl of that vector field will give you different values. If the curl of the vector field is quite large, then the vector you're representing is like a rotating vector field. In static charge distribution, like that the electric lines of force are always a straight line. Okay, so like for example, if you have positive charge here, static charge distribution means charge is stationary. If you consider stationary charge particle, in a stationary charge particle, the electric lines of force are pointing, diverging like this. The electric lines of force are diverging away like this in stationary charge distribution. Or if it is a mass of Q, then the electric lines of force are pointing towards the negative charge. The electric lines of force are pointing towards the negative charge. So the electric field at any point is tangent to the electric lines of force. All right. So in this case, the electric lines of force are also, electric field is also a straight line. Electric lines of force are pointing towards negative charge in stationary charge distribution, and here also pointing away from that. And at every point here, the electric field is tangent to the lines of force. So the electric fields are also converging here in this case, and here is this diverging. There is no rotation of the electric field here, right? So because of that, in static charge distribution, the curl of electric field is 0. Curl of electric field is 0. But later on, you will find that when we have a moving charge, non-static charge, when you have a moving charge, like in the case of electromagnetic induction, Faraday's law, you will find that curl of electric field is non-zero. Actually, according to Faraday's law, curl of electric field is minus of del B upon del T. Okay, this is the differential form of Faraday's law. In that case, Faraday's law is a case in which you have a non-static moving charge. All right. So on the other hand, magnetic lines of force originate at North Pole and terminate at South Pole, and there is a rotation, as you have seen already here. Where is that? Yeah, over here. Magnetic lines of force is rotating field, right? In this rotating field, uh, there is a rotation, means curl of B is non-zero. Curl of B is non-zero, and there is this fundamental law on magnetism called Ampere's law. I think everybody is aware of Ampere's law. Ampere's law in differential form is actually curl of B is equal to mu J vector. J is the current density, mu is the permeability of the medium. This is Ampere's law in differential form. Okay, so since the magnetic lines of force, the magnetic poles always exist in pair, and one from North Pole it originates and rotating around and converging at South Pole again. Therefore, it's a rotating field, right? Magnetic field is. So curl of B is non-zero, and the quantity that is curl of B is given by Ampere's law, which is mu into J vector. Current density, J vector, and permeability of the medium mu. So I hope you know what we mean by this curl of a vector field now. So these are some like simple vector algebra. This is something which you have to practice yourself also. So here this is ln. Ln means natural logarithm. Natural logarithm. So whenever you write ln means it is equivalent to log to the base e, natural log, right? So r is the position vector in space, like I discussed before. R is a position vector in space. It can represent the location of a point in the space. This is x exists, y exists, z exists. So any point in the space, the position of that point, the vector defining the position of that point is what we know it as a r vector. So what is r vector? R vector is, if you drop a perpendicular here, the coefficient of the x coordinate is x, the coefficient along the y coordinate value is, let's say, y, and the coefficient along the z coordinates is, let's say, this is z, right? So therefore your r vector is xi plus yj plus zk, okay, right? So whenever you take a magnitude, so when you simply write r without any vector, that is representing the magnitude of the vector r. Magnitude of the vector r is square root of x square plus y square plus z square. Okay, without this unit vectors. When you take the magnitude, square root of the coefficient x square, y square, and z square. Like if you have a vector a1, a here, a1 I cap plus a2 j cap plus a3 k cap. If you are going to take the magnitude of the magnitude of the vector is simply square root of a1 square plus a2 square plus a3 square. So I think everybody knows already. So that's how we take the magnitude. So when you take the magnitude, this is what you get, and this is simply to the power 1 upon 2. So ln natural log, if you take a log of this thing, ln of this thing, this will be, you know that ln of e to the power x is x into ln of e, right? Or ln of a to the power 2 will be 2 ln of a. So I hope you know this logarithm formula. So if you take a if you look at this ln of this vector, magnitude of this r vector will be scalar. This quantity is scalar, right? This quantity is scalar. There is no vector sign here. This quantity is scalar. So you take the gradient on that, gradient of the scalar quantity. So this is the del operator operating on this scalar quantity. Now this scalar quantity, you will have to multiply with this thing. That means differentiation of this scalar quantity with respect to x, differentiation of the same quantity with respect to y and z. So you just perform the differentiation. So I think I don't need to revise all this calculus. So I think everybody knows that differentiation of ln of ln of x cube will be something like this. Differentiation with respect to x means 1 upon x cube into differentiation of x cube with respect to x. So this will be 1 upon x cube into 3x square. So I hope you know this. So if you do that, differentiation of ln of this would be 1 upon this, and then differentiation of this quantity will be differentiation of y square and z squares are with respect to x are 0. Differentiation of x square with respect to x is 2x. So if you follow that simple calculus, then finally this is what you get. This is your vector itself, and this is your r square, because your r is square root of this. So x square plus y square plus z square will be your r square. So I think you should be able to follow this if you are familiar with this kind of calculus, but you are expected to know the calculus, right? So this is also something similar. Just a minute, I need to mute for 1 minute. Anyway, let us continue because I was trying to call my either my mom or dad. They are in upstairs, so let's see when I can connect to them. Otherwise, we can continue. Okay. So this particular case is also gradient. So this r is again the position vector. So you just take the magnitude of that r. This is the small letter r without any vector sign, and 1 upon r is this, and this is simply x square plus y square plus z square to the power minus of 1 upon 2. So uh, similar to what we have done before, when you take a gradient, this will be operated by this del upon del x, and del upon del y operation also will perform on that. Del upon del z operation also will perform on this, and then you just take the differentiation, simple differentiation, and this is what you get. Okay, so this is simple. uh, Now let's see this Laplacian operator or scalar operator. It's also called a scalar operator in the sense that when you take a single del operator is a vector operator because of this vector sign here, because the resultant of this del operator operating on a scalar quantity is a vector, right? But Laplacian is a del square operator. Del square means del dot product between del operator two vector operator. When you perform a dot product, the resultant is a scalar operator. So this is like this: I dot I cap dot I cap is 1. Therefore del square upon del x square, you have the first operator. I dot j cap is 0, I dot k cap is 0. And now if you look at this, j dot I is 0, j dot j is 1. Therefore del square upon del y square, and similarly del square upon del z square. Now this also again you can perform this r your position vector. You already know position vector, you already know xi plus yj plus zk. So you take the magnitude like I explained before, and 1 upon r is this. You perform this del square operation. So if you perform a del square operation on this this scalar quantity, and all of these are scalar quantities. So scalar operator operating on scalar quantities. So this you have to operate with this you have to operate with this and this. So it's a double derivative. So this is simply again a simple calculus. This is just a differentiation. If you differentiate it once, this is what you are going to get, and differentiate it again using differentiation by product rules. Differentiation of product rules, you know that this is, let's say, f and g, two functions you differentiate. So differentiation of second function with the first function plus differentiation of first function, like this. So it's a differentiation of product rules. You just follow that and you will get the result. Okay, I don't want to get into that detail. Now this is another vector identity which you should always remember. Here phi is a scalar quantity, a is your vector field. So if you're going to take divergence of product of phi and a, this is how it's going to be like that. So phi into a means phi is a scalar, a is a vector. So when you multiply scalar and vector, you have to multiply all the components of a vector. You have to multiply all the components of a vector with a scalar. Whenever you multiply scalar with a vector, this scalar quantity will have to be multiplied to all the components of the vectors. So when you multiply to all the components of the vectors, this is what you are going to get, right? So when you take a divergence like this, I dot I is 1. So del phi a1 upon del x, j dot j is 1. del phi a2 upon del y, k dot k is 1 del phi a3 upon del z, right? So again, a1 is now, as I said before, a1 is the coefficient of I cap. It could be a function of x, y, and z, like I already mentioned before. A2 could be a function of x, y, and z. So considering that, uh, if you have the product of phi and a, phi is also a function of x, y, and z. So it's a product of two functions of x. So you just follow the differentiation by product rule. First, differentiate the first function, multiply with the second function, plus differentiate the second function, multiply with the first function. So differentiation by product rule, you just follow it here. This is what you're going to get. And you combine this term here. You combine this and this term over here. So what you have here is uh, this is a product of two vectors. Here you can see that, like I explained before, if you have two vectors a, b, like this, a1 I cap plus b, sorry, a2 j cap plus a3 k cap, dot product with b1 I cap plus b2 j cap plus b3 k cap. So if you take a dot product here, what you're going to get is a1 b1 plus a2 b2 plus a3 b3. So if you have this term and this term, this term and this term, you can see that this is actually del phi upon del phi upon del y, del phi upon del z, dot product with this. So del phi upon del, this term is your gradient of phi, and this is your vector a. And over here, this is the, if you look at this, phi as a common factor, you take it out, and this will be this operating on this vector, divergence of a. So I hope you know what it is now, because I've shown you divergence of a. So this is a vector identity which you should remember. Okay, so this is the proof of that. And this is also another vector identity which is also very like relevant in many engineering and physics calculation. So phi is a scalar quantity. So when you take a grad phi, this is a grad phi, and when you take the cal again on that grad phi, so I j k, del operator is del upon del x, del upon del y, del upon del z. Cal means this term also, del phi upon del x, coefficient of j cap, here in this case the second vector. Grad phi is like the second vector. In the second vector, the coefficient of j cap is del phi upon del y, and the coefficient of k cap is del phi upon del z. So you have to put it like that. And if you follow the cal formula, the cal that we have already discussed, I coefficient will be this quantity operating on this. So del square phi upon del y del z minus this quantity operating on this del square phi upon del z del y, and similarly you will get this and this. And we know that phi is a scalar quantity. In a scalar quantity, whether you differentiate first with z and then perform differentiation with y, or you first perform differentiation with y and then perform differentiation with z, it does not matter. So you will get the same result. If you interchange the order of differentiation with respect to the space variables, you get the same result. So they are identical. So they will cancel out, and similarly this cancels out, and what you're going to get is cal of a gradient of a scalar field. Any scalar quantity you take, cal of a gradient of that scalar quantity is always 0. Okay. So this is also another very important vector identity. Here A is a vector field. This is like, you can pronounce it like, this is divergence operation, and this is cal. That means divergence of cal of a vector A. Okay. So now A is a vector. This is del operator. When you perform a cal, first you calculate this cal. When you perform a cal, this is what you're going to get. Then you perform a divergence. Divergence means this del operator dot, here del operator dot product with cal of a vector. Cal of a vector is this quantity, so you put this quantity as the cal of a. So I dot I is 1, right? So this del operator operating on that, del upon del x, j dot j is 1, j not this not z cap, this is k cap, k cap dot k cap is 1. So I dot j, I dot k, they are 0, because this we have already discussed. You should always remember that I dot I is 1 and j dot j is 1 and k dot k is 1. However, dot product with I dot j is 0 and sorry, I dot j is 0, I dot k is 0. So because they are orthogonal vectors, I, j, and k, they are pointing along x-axis, y-axis, and z-axis. They are orthogonal vectors. The angle between them are 90 degree, right? So because of that, their dot product is 0. Because cos 90 is 0. We know that. So if you perform this, the first term you have del square a3 upon del x del y, and over here, uh, del square a3 upon del y minus you have. So these two terms cancel out, and similarly this and this will cancel out, and this and this cancels out. And eventually he will find that for any vector field A, divergence of curl of the vector field is 0. So the reason here is that curl of A will measure the rotation of the vector field. If A is non-rotating vector, curl of A is 0. So it does not matter when you perform a divergence again. Okay. But if curl of a vector A is finite, that means vector A is a rotating field. But when you perform a divergence on a rotating field, then again this is 0. So the divergence of curl of A is always 0 for any vector. And this is your assignment. Take curl of vector A and see that this is equal to this quantity. So this vector identity is also very, very important. This is something you should not, you should always remember. This vector identity is very, very important. And again, this vector identity is also very important. We will often use it in physics and engineering calculation. Hey, off tomo, wala, tui pam khay off. Khay mai lo tui liam ni cho, ori cho. Okay. Vale. Class ka laklo, deo ken to so. Okay. Now, this is the last topic which I plan to discuss for today, because next will be divergence theorem that we will do it next week. Now, here, so that gradient of any scalar quantity, gradient of a scalar field is a vector perpendicular to the surface represented by this vector. If you look at this, this is a little bit vague. So this is x-axis. Let's say this is y-axis. Let's say this is z-axis. Unit vector along this axis is I cap. Unit vector along this axis is j cap. Unit vector along this axis is k cap. Okay. Now let's say we have a certain plane like this. Let's say we have a certain plane, and this plane intersects the z-axis at, let's say, 1, 2, 3. Let's say this is where the plane intersects the z-axis, that is at z equal to 3. Okay, it intersects the z-axis at 3. So if this is an infinite plane, that means it extends in this direction, extends in this direction up to infinity, extends in this direction up to infinity. When we have a fixed plane, the equation of this plane will be z equal to 3. Equation of this plane, equation of the plane will be z equal to 3. Why do I say that z equal to 3 is the equation of the plane? Because for every point on this plane, if you take any point on this plane, z value will be 3, because we have a plane which is parallel to xy plane, right? It is parallel to xy plane. So from xy plane, the height of that plane is always 3. The height of the plane is always 3. So for every point on this plane, z value is always 3. So this is the equation that defines this infinite plane. So if you compare with this here, phi equal to c, that means here your phi is 3. Your phi is z, your c is 3. Right. So now if you take a grad of this, grad phi will be I del upon del x plus j del upon del y plus k del upon del z. Phi is z, right? So differentiation of z with respect to x is 0. Differentiation of z with respect to y is 0 plus k cap. Differentiation of z with respect to z is 1. So grad phi, as you can see, this is equivalent to k cap. Grad phi is equal to k cap. See, that's exactly what you can see here. K cap is a unit vector pointing along the z-axis. K cap is pointing along the z-axis, right? So as you can see, k cap is a vector perpendicular to z equal to 3 plane. K cap is a vector perpendicular to z equal to 3 plane. So this is what we are trying to prove. Here, for this particular plane, we can find that grad phi actually represents a vector which is perpendicular to the surface. Grad phi actually represents a vector perpendicular surface because k cap is a vector perpendicular to the surface z equal to 3. So if z equal to 3 is the equation of this surface, k cap represents the vector perpendicular to the surface, which is actually your grad phi. Yeah. Now, this is something we have discussed again before. This is x, y, and z. And if you take any point here or in the space, the position of that point is represented by position vector r. And if you move in this direction, the small changes in the point is represented by dr. So the resultant vector here is r vector plus dr vector. Similar to that, now if you represent any point on the surface as using this position vector r, if you move from one point to another point in the space in this surface, let's say this point, this is, if you move to another point on the surface, this is, let's say, your dr vector here will be, dr vector will lie on the surface. Dr vector will lie on the surface of the plane. Okay, dr vector will lie on the surface of the plane, or dr vector will be tangent to the surface. The surface. So remember that dr vector will be tangent to the surface. All right. Now let us continue. So let's say we take r as a position vector. We already know this is the position vector of any point on the surface phi. So we, in the earlier case, for simplicity as an illustration, we have considered a flat surface. So we can actually have any kind of arbitrary surface like this. Okay, arbitrary surface. So let's say we have a surface like this, and we take dr r vector here be the position vector of any point on the surface, represented by this phi x y z equal to c is the equation of the surface. Dr will be a tangent vector to the plane of the surface. So if you take a dr vector here, so if we move to another point on the surface, dr vector will be a tangent, or it will be parallel to the plane of the surface. Okay, tangent to the plane means it will be a vector which is parallel to the surface. Now Here, the equation of the surface represents that phi x, y, z is constant on the surface. Phi is constant on the surface. So since phi is a constant, any change in phi on the surface, any change in phi on the surface, d phi on the surface is also 0. Okay, so if you're moving from one point to another point on the surface, d phi, change in phi is 0 because phi is a constant. This is the equation of the surface. Like over here, for this infinite plane, z equal to 3 is the equation of the plane because z value is constant for every point on the surface. So if you move from one point to another point on this planar surface, z value is always 3. So that means change in z, dz, as you move from one point to another point on the surface, change in z, dz value is always 0. Similar to that, you take any arbitrary surface. It could be a curved surface, it could be a cylindrical surface, or it could be planar surface. We are just considering any general surface which is defined by this equation phi x, y, z equal to c. And we are considering that r to be the position vector of any point on the surface. And here, like I explained before, dr will be when you move from one point on the surface to another point on the surface, the change in the position vector is your dr here, okay, which is represented like this. And uh, as you move from one point to another point on the surface, your phi value is, change in phi is 0 because this is the equation of the surface. Like we discussed here, z equal to 3 is, z is constant on this surface. So we are considering, to represent the equation of surface, we're considering some quantity, some functions, scalar functions, which is constant. Now, using partial derivative law that we did explain before, phi if is having a dependency on more than one variable, so we can write it like del phi upon del x into increment on x, del phi upon del y, how quickly phi changes with y multiplied with increment on y, and similarly this. So using the dot product rule, you can again separate out these two terms consisting of this and this. And the first term, as you see, it's a grad of phi, and the second term is, see, this is dr. Dr is tangent to the surface, or dr is on the plane. Dr is on the plane or tangent or parallel to the surface. Right. Dr is on the plane or tangent or parallel to the surface. All right, like I discussed. So if you take a dot product here, this will be magnitude of grad phi, magnitude of dr into cosine of the angle between them. So as you see, the dot product between these two vector is 0. The dot product between these two vector is 0 only if theta is 90. That is, the angle between dr vector and grad phi is 90 degree. All right, so that means we know that dr is a vector lying on the surface of the plane at that particular point, and then this is perpendicular with grad phi, means grad phi is perpendicular to the surface. Okay, grad phi is perpendicular to the surface. I hope you get the idea, because dr is tangent or parallel to the surface at that particular point represented by your r vector. Therefore, since the dot product between dr and grad phi is 0, that means grad phi is 90 degree, at 90 degree to the surface at that particular point represented by r vector. All right. So that's it for today. I will stop here, and I will have to split the lecture video into two parts, and then after that I will upload. So from tomorrow we will study divergence theorem, Gauss divergence theorem, and yeah, some proofs and all. Not tomorrow, maybe on Friday. We'll see if it's convenient to take a class in the evening. Yeah, I'll stop now.